Greetings everyone. Welcome to Kite lecture series. And today we will be discussing about virtualization. So let's start. Okay. In previous video, we have already studied about the definition of virtualization and what are the types of virtualization. In this video, we would be studying about the implementation levels of virtualization. Now, in this video series of virtualization, we would be studying about implementation levels of virtualization, virtualization structures, tools and mechanism, virtualization of CPU, memory and IO devices, and the last one is virtualization support and disaster recovery. So these are the four major topics that we will be studying in this virtualization series of cloud computing. In this video, we will be focusing on implementation levels of virtualization. Now, so basically, virtualization technology enables the use of multiple virtual machines that could be run on same set of hardware host. Means on hardware level, there's a single machine and you have an ability to run multiple virtual machines on that, right? And if we talk about a computer system, it contains many levels. So in this video, we would be studying on what levels you can actually implement this virtualization technique. Now, we have divided this computer system into 5 layers. If we talk about the lower layer, it is known as instruction set architecture. Now, this is one of the basic and the lowest level layer. In this layer, the compilers and assembler work, right? So just above that, we are having hardware abstraction layer. Now, in this layer, we would be utilizing all the hardware resources and we would be implementing the virtualization on hardware, right? And on the top of that, we would be implementing virtualization on operating system level. And just above operating system level, there are 2 layers, application level and library level. Now, we all know that application runs by using operating system, and operating system acts as an interface between application and your hardware. So in order to interact with operating system, application uses certain APIs and libraries. So that's why just above the operating system there are 2 layers. One is the library layer and the another one which is at the top is application level. So on these 5 layers we are going to implement the virtualization technique. So let's start. So the very first layer is instruction set architectural level. At ISA level, the virtualization is performed by emulating a given ISA by the ISA of host machine. So here the emulation process is being done by the ISA of host machine. In instruction set architectural level, basically this is, as I have said before, this is the lowest level. So in this level, assembly languages and you can say compilers work. And as you all know, the language which are used in this layer is totally machine dependent. I mean, the assembly language is actually dependent on the type of processor that we are using in. If you know about the assembly language or if you know about the binary language, all these languages are machine dependent and these languages vary machine to machine, right? So you cannot just take the assembly level code from one computer and run it on the another computer which may be having some different hardware architecture. So if the hardwares are different, you cannot run that same, you can say that same assembly. So the one of the basic advantage of using virtualization layer on instruction set architecture level is that you can actually emulate a given ISA by the ISA of host machine. It means Say for example, I'm having a binary code, MIPS binary code that actually runs on your MIPS based host machine, right? But if after implementing virtualization on instruction set architectural level, you can actually run MIPS binary code on x86 based host machine with the help of ISA emulation. With this approach, it is possible to run a large amount of legacy binary code written for various processors on any given new hardware host. Now, this is a very great thing because all these binary languages, binary code, and your assembly level code are machine dependent, and you cannot just move one code to another. But due by this virtue of virtualization, you can actually make these codes run as if they are machine independent. Now, the basic emulation method is through code interpretation, and you all know what is an interpreter program. An interpreter program interpret the source code line by line. So here they are saying that interpreter program interprets the source instruction to target instructions one by one. So yes, here if you want to run MIPS binary code on an x86 based host machine, there are certain instructions and you have to translate that instructions into x86 based host instructions, right? So here interpreter is reading all those source instruction and translating it to target instruction one by one. Now, this is also a very slow process because one source instruction may require tens and thousands of native target instruction to perform its function. It means in order to translate one source instruction, 10 to 100 native translation instructions would be used just to perform that functionality. I mean, just for the sake of translation, just translating the functionality of one source instruction, it actually requires 10 to 100 native target instructions to perform its function. So it is a very slow process, and to make this process better or to improve its performance, we are using dynamic binary translation. We will be studying dynamic binary translation in detail in the next videos. For now, you just need to know that it is an approach that translates the basic blocks of dynamic source instruction to a target instruction. Now, by this technology, you would be able to translate the block of instructions that are source instructions to the directly into the translate instruction. Rather than scanning and translating the line one by one, it translates the block of dynamic instruction to a target instruction. Now we can increase the size of blocks so that we can increase its translation efficiency, right? Now, a virtual instruction set architecture thus requires adding a processor specific software translation layer to compiler. Now, what they are trying to say is, if you want to increase the performance, rather than relying on an interpreter, we can add a processor specific software translation layer to a compiler. So if we add this virtual instruction set, that this virtualization translation layer in the compiler, it would be easy because, as you all know, interpret converts the line one by one, whereas compiler converts the line into binary code in just one go. So that was all about instruction set architectural level. Now let's talk about hardware abstraction level. In hardware abstraction level, the virtualization is performed right on the top of bare hardware. It is also known as bare metal hardware. So in this type of virtualization, the virtualization layer don't need any operating system. We are adding this virtual layer on the hardware layer. right? So here the virtual layer is having two tasks. At one hand, this approach generates a virtual hardware environment for VM. So the task of this virtual layer is to generate a hardware environment for VM. On the other hand, the process manages the underlying hardware through virtualization. Now it's having the second task is that it has to manage all those hardware through virtualization. First, it generates the virtual environment. Second, it has to interact with those hardware so that it can satisfy the demand of the virtual machine. The idea is to virtualize computer's resource such as its processor, memory, IO devices. The intention is to upgrade the hardware utilization rate by multiple users concurrently. More recently, Xen hypervisor has been applied to virtualize x86 based machines to run Linux or other guest OS applications. Let's talk about the advantages. Just because it is at the lower layers, that's why you can say it has high performance and good application isolation. One thing that you need to understand is that whenever any control is at the lower level or at the lower layers, it would be having high performance because it is very much close, it is very much near to your hardware, right? So that's why it is having a very high performance and it is having a very good application isolation. One of the shortcomings of this approach is that it is very much expensive to implement and it is having very much complexity. So cost wise, it is not that feasible. From hardware layer, we move to the operating system layer. Now, this is a very interesting concept because in this they are actually sharing the kernel, which means that these virtual machines are not having their own kernel, but they are sharing their kernel with host operating system. OS level virtualization creates isolated containers on a physical server and OS instance to utilize the hardware and software in data centers. The containers behave like real servers. OS level virtualization is commonly used in creating virtual hosting environments to allocate hardware resource among the large number of mutually distrusting users. One of the advantages of this virtualization and operating system level is that it is having minimum initialization time. It means it can start up and shut down very easily, and it is having very low resource requirement because they are sharing the kernel, so they itself don't have any kernel, so they have a very low resource requirement and they have a high scalability. You can make many virtual machine with this type of system, right? Here we can see we are having 3 virtual machines and all are sharing this kernel of host operating system. Now there are certain shortcomings as well. All VMs at the operating system level must have same kind of OS. Now this is a very crucial shortcoming because if you are sharing the kernel of host operating system, then the operating system that virtual machine is having is also the same. It means if you are sharing the host operating system is of Linux, so basically this would be a Linux kernel. And what I'm trying to say is you can only have the virtual machine which are Linux based. You cannot have a virtual machine which is having a Windows operating system or which is having a Mac operating system. You can have Ubuntu, you can have Fedora, but all I'm saying all these operating systems because they all are having same kernel. Now let's talk about library support level. Since most systems provide well-documented AIs, such an interface becomes another candidate for virtualization. Now, virtualization with library interface is possible by controlling the communication link between the application and the rest of the system through API hooks. Now, as we all know that applications which are installed in a particular OS, those applications communicate with OS or communicate with the hardware with some APIs, with some libraries. And right now at this stage, in this particular scenario, we are actually virtualizing at library level. So what are the advantages of that? it has very low implementation efforts. And one of the example of this library support level is Wine tool. If you are a Linux user, then you must have heard about this Wine tool. Wine tool helps to run Windows based application on a Linux server or on a Linux system. So as we all know that applications which are installed in a particular type of OS communicate with that OS with all these libraries and APIs. So adding a virtual layer at this library level will help us to support all those applications which may or may not be developed for that host OS. This is Wine is the perfect example of that. Now, one of the advantages of library support level is that it has very low implementation efforts. So you just have to change the APIs. You don't have to change the application. You don't have to change the host operating system. You just have to change the APIs. So that's why it is having a very low implementation efforts. Now, the shortcomings of this library support level is that it is having poor application flexibility and isolation. Why they are saying this? Because not every application comes in this picture. We cannot virtualize each and every application. There are certain exceptions, and we can use this type of virtualization with some limited set of applications. The last one is user application level. Virtualization at application level virtualizes an application as a virtual machine. On a traditional OS, an application runs as a process, right? Therefore, the application level virtualization is also known as the process level virtualization. The most popular approach is to deploy high-level language virtual machines. In this scenario, the virtual layer sits as an application layer on the top of operating system, and layer exports an abstraction of virtual machine that can run programs written and compiled to a particular abstract machine definition. Other forms of application level virtualization are known as application isolation, application sandboxing, and application streaming. Now, you might have heard about sandboxing. If you have if you have an Avast antivirus in your system, there is an option of application sandboxing. What they do is, if Avast antivirus feels that this type of file is not suitable and it can potentially harm your system, so it will run that file in a sandbox. Sandbox is a virtual environment where file runs, and even if that file is malicious, it won't harm your system because the file is being run in a virtual environment which is known as sandbox. So here as you can see, in application level virtualization, application isolation and application sandboxing is done, where the application is separated from another application and it is being run on that environment where it cannot directly interact with other applications, or it cannot directly interact with operating system or system hardwares, right? Now, application streaming is one of the good example. In application streaming, what happens is that when you run an application, only the essential part, so first of all, you have some executable file, and when you run that executable file, it triggers a communication to the host server where this application is actually hosted, and at the time of initialization, only the important files, not the entire application, only the important files, gets downloaded and your application runs. And whenever you require some additional features of that application, those features get downloaded on demand. So in application streaming, the whole application does not reside on your local machine. Only the specific or the important part of that application reside on your local machine, and that too on a temporary basis. When your task is done, that file gets deleted. The advantages of user application level is that it has best application isolation? Yes, obviously sandboxing technique and application isolation technique is the best example of application isolation. Okay, so advantages are it has best application isolation. Obviously sandboxing technique is an excellent example of application isolation. And shortcomings and limitations are it is having low performance, low application flexibility, and high implementation complexity. These type of systems are very complex to develop, and they are having low performance and low flexibility is because one thing that you need to know is that whenever the more virtualization is at the lower levels, higher would be the performance. If the virtualization is at the higher level, then there would be some lagging in performance. That's all for today, guys. Thank you so much. Today we have discussed the implementation levels of virtualization: application level, library level, operating system level, hardware abstraction level, instruction set level. All these are the 5 operation levels of virtualization. Thank you so much, guys. We will cover the next 3 topics in the next video. Till then, stay fit. Jai Hind.